Good morning, everybody. Thanks for coming out for the dedication of the Mike Prime Room here at Hill Engineering. As you know, and as Adrian told us earlier, Mike has a long history of connection with our research program, the general area of residual stress and performance of the mechanical behavior of materials. So it's a great pleasure to have my friend Mike here for the first time visiting Hill Engineering in our new building and visiting the Prime Room. And Mike's going to talk to us about the history of the contour method. So let's give it up for our good friend, Dr. Mike Prime.
Thank you, Mike. I'm pretty excited to be here. I've never given a talk before in a room with my name on it. I think I could get used to that. When I talked to Adrian about what to talk about here, we both had the same idea to talk about the history of the contour method. So that's kind of what I'm going to do. And you see the title there, the first and nearly last contour method measurement. So really it almost didn't happen, and I'll explain to you why. And I'm going to use this opportunity to tell some parts of the story I've never told before. I figure you guys are an audience that might appreciate it. So even some of the stuff even Mike hasn't heard before. Hopefully it's entertaining. My outline, I'm going to talk about the first contour measurement, and I'm going to do rambling diversions on whatever I feel like. I figure you guys are a captive audience. So I got a few things I'll talk about. First, the backstory. I got my PhD and ME from Berkeley in '94. And I did do my dissertation on residual stress measurement. Worked with Ian Finney, who was my advisor, and Willie Chang. You guys have probably seen Chang and Finney papers if you read that stuff. Willie was, I think, a postdoc for a while, then a researcher. Very brilliant guy. Very impossible to get anything out of it. I had a hard time learning the slitting method when I first learned it from Willie. Went to work for Los Alamos in '94, and the first year or more I worked mostly on damage detection with vibrations, looking for cracks and parts and things like that. Nonlinear vibrations mostly. Mostly that was what I was working on. I got back to residual stress a little bit in '95. We had a CRADA at the lab. CRADA is Cooperative Research and Development Agreement with General Motors. And they were worried about distortions in their gears, case-hardened gears. And they were trying to measure that residual stress. They had a bunch of guys doing X-ray. And they took the parts, sent it around to a bunch of X-ray labs around the country, and got results all over the map. Now, Mike's not going to be surprised. You guys probably aren't either. We've seen that kind of stuff before with X-ray diffraction. They were quite worried, so they asked if I could measure the stress in this thing. Somebody remembered the talk I had given when I interviewed for the job. So this is the gear blank. Put on some strain gauges. Did EDM slitting from the outside in through the case-hardened layer. And these are the results we got. The blue curve was the residual stress from that slitting measurement. Compared with some FEM and a surface X-ray measurement. Got very nice results, and it really saved them on this project. They were really having a hard time getting believable results. So because of that, I got some internal funding, which we call LDRD, Lab Directed Research and Development, to develop the slitting method. 3 years worth of funding for part of my time to work on that. During that time, I made the crack compliance, or what we now call slitting webpage, in about '95 or '96. And that I don't know if you guys have seen that web page is still there. It's evolved a bit, but it's the same basic web page. Matter of fact, the first picture on the web page was this. And I got an email around then from a grad student from Stanford. I think I've got a picture of the email. How did that get in there? that's Oski stomping that pickle or whatever that Stanford mascot is. This is the email from Mike I got in April of '96. He had seen the web page and asked a question about waterproof coating on the strain gauges. That's how I first met Mike. I hung out with Mike in Sweden in 1997. The International Conference on Residual Stresses was in Linköping, Sweden in '97. And we roomed together and hung out in Stockholm. There's a picture. Nice shorts, Mike. Yeah. Had a real good time. And if you ever get the chance, these are great conferences. The International Residual Stress Conferences, I think they're fantastic. All kinds of people working on residual stress, doing great work. So as part of the LDRD, I did a literature review on slitting, on the slitting method. I looked up all the references I could find. And as part of that, I found this conference paper from a guy working on railroads. And you can see the title there. They did saw cuts and measured displacement on railroad rails. And what he did was, here's the wheel. Actually, the measurement was on a wheel. Did a saw cut from the outside radius in, so that's the edge of that saw cut. And he had made marks on the inner and outside, this front surface and then the back surface of the wheel, made some little marks, measured how far apart they were, cut partway through the wheel, and measured how far they moved. And then he took those readings, interpolated them a little bit, and did a finite element model and forced it back flat. And he says here, it might be right, but he's not sure if that's the right answer. And so I referenced this article in Slitting Literature Review, which was a Lannel report in '97, and it was published a couple years later in Applied Mechanics Reviews. And I didn't think much about it after that paper I had read. I was writing a talk for some conference, a talk on the slitting method, and we often talk about how we get the compliances, the coefficients, right? And we use Buckner's principle. I took this picture from my advisor's course notes. So this is standard Buckner's principle. A is a part that's got residual stress in it, stresses you don't know. If you cut a slot or a crack partway in, and the stresses redistribute and it deforms. If you take the original stresses on that cut face and apply them to a cracked part, you add those two stress states together and you get back the original stress state. That's the basics of Buckner's principle. For doing coefficients, like for the slitting method, what you want is B. You want to know how much it deforms, right, when you put in a slot. So the answer is it's A plus minus C. So you take a model with the crack, apply those original stresses to the cut face, and measure how much it deforms. The deformations in A are 0, so those don't matter, right? So this is how you get that deformation. As an aside, this was an important early problem for fracture mechanics. So they want to know the stress state around a crack tip. This was in the late 50s. So it was before FEM was capable of doing this kind of calculation. And so they were trying to do analytic methods to solve that. And and the question of, as you increment a slit, the stresses redistribute as you go, right? And each increment of the slit, you're not relaxing the original stresses. You're relaxing some kind of change stress. It's conceptually hard to figure out how to do that. And this method tells you that all you need to know is the original stresses. You apply the original ones, not redistributed stresses, to calculate that deformation. Not obvious. To me, it wasn't obvious. Not intuitive. But it was a big deal for fracture mechanics. I've often referenced Buckner's paper where he proved this. And I've had over the years quite a few emails and calls from grad students around the world who are upset because there's no figure like this in that paper, and there isn't. It's mostly written text. The first time a figure like this appeared, there was a paper in '61 from Barenblatt where he talked about fracture mechanics solutions, and he published a paper like this and credited Buckner for having proved it. And that's actually how my advisor, who kind of invented the crack compliance method, that's how he found this, was in that paper from Barenblatt. As another aside, there's a very similar figure to this in Paul Paris's paper on fatigue crack growth. So Paris's law, dA to the n is C delta K to the n, very famous paper. He's got a figure like this he used to calculate that delta K for fracture mechanics. If you guys, for fatigue crack growth, if you don't know the story, and I won't spend too much time, that paper was published in the engineering alumni newsletter for University of Washington because nobody would publish it. And it was a really quite brilliant piece of work. People still to this day refuse to believe that Buckner's principle works correctly, that you get redistributed stresses that calculates that effect correctly. We see papers in literature every couple of years where somebody says it doesn't work. And it's just because they don't understand. It does get used wrong sometimes as well. I've seen people use this for hole drilling and for slitting to calculate yielding effects, to look at plasticity, where they'll do this kind of calculation to calculate yielding at the crack tip. And for something like yielding, you can't ignore the stresses here. The deformations here are 0, so you can ignore it for that. The K1, the fracture, the stress intensity factor is 0 because there's no crack there. But the von Mises stress in this stress state is not 0. So if you use this to calculate a yielding effect, you're missing part of the stresses. People do that as well. So you got to understand what this principle can do and what it can't. Also, and this point is when I had this idea I could do something different. This is that first line of that superposition principle, and you're superimposing stresses, right? And I was thinking maybe about that Jorm's paper, but if you measure the shape on that cut face, right, could we apply, instead of a stress, apply a displacement here, force it back flat displacement-wise, and get back the stresses? And I thought about that, and there's no reason that shouldn't work. It's a Kirchhoff boundary value problem. You can swap out stresses for displacements for a boundary condition. Should work totally correctly. And I realized, of course, right away, if you did that, you could measure stresses all along that. You could measure displacements all along that cut face and not make a 2D assumption, but get a 2D stress field in a 3D part. So that was kind of where the idea came from, was actually looking at this figure for a slitting paper. What about the stresses in B? There's 0 on the cut face for that normal stress. So this alone will give you that stress on the cut face, right, is why it should work. I was pretty skeptical of this idea that it would work. A measurement on the cut surface would be really a fundamental difference for standard experimental mechanics. Almost everything we do, you take a reference measurement, you take a 0. You measure what something is before you deform it, then do your deformation and measure the difference, so you get a displacement. We have no reference there, right? That cut surface is not there beforehand. We're just going to measure a shape and infer displacements. If you do that, it can give you that 2D stress map, so I knew that it could be quite powerful. And it's a much simpler inverse solution than we use for slitting too. So you can kind of double up with benefits if it worked. The displacements are often small, less than 10 microns, and we have no reference state. So I was quite worried that signal to noise would be too small. We'd never see those displacements. Figured there was no harm in trying, and I might learn something, so I thought I'd give it a try. So the first question was how to measure that shape. And I spent 2 months, this was a side project of a side project, so it wasn't the main part of my time. I spent a couple months trying to figure out how I could get an instrument inside a slot and measure that shape. And I went all over, the lab's a big place, Los Alamos, went all over, asked people to get anything that can get inside a slot and measure that displacement. Guys talking about miniature lasers and all kinds of stuff. Never found anything that worked. And finally, after a couple months, those weren't supposed to be on there. I finally figured out, why don't I just cut it all the way in half? Took me a couple months to get there. And I put this figure on here, this is from a newer paper, but this is a figure of Buckner's principle again, from an FEM simulation, just to kind of reinforce what we're doing here. And this is a model where the parts got stresses X and Z, which is out of the plane, are equal. Tension, compression, tension. You cut it in two. The normal stress on that surface goes to 0 if you look at the scale here. The Z stress, which is the out-of-plane stress, doesn't go to 0. If you measure that shape, force it back flat elastically, and add this stress state to that one, you get back that. For the other direction, the summation still works, but it's not 0 here, so you'd have to measure this as well, which is something you guys do with your, what do you call it, biaxial mapping, right? Is use kind of this basic principle. It's worthwhile understanding really how Buckner's works in total. All right, so just cut it in half. I had a specimen readily available, so we had been making these plastically bent beams to make a known stress specimen for the slitting method, and had published that. Here's the slitting test. We cut EDM, same thing you guys do. There's the strain gauge. This is after the cut. There was a strain gauge on the top surface as well. And we had published all that. And there's the black line is the prediction from the bend test. Red line is the slitting result. We did neutron diffraction. X-ray diffraction, which we did kind of along the surface there, which is noisy because this thing had pretty big grains in it, but they all match. So a very well characterized specimen. Know what the stress is. It wasn't cut all the way in half for slitting. You know, we usually stop before you get to that back strain gauge. And so what I did was I took the thing and I actually just snapped it in half that last little bit. Probably not the best way to do it, but if you're going to do it. That's actually not the surface from the original specimen. I grabbed another picture here. So I had to measure that surface height. I didn't know how to do that either, how to get a surface height map. Asked around the lab, and somebody said, well, I've got a profilometer, one of these things for measuring surface roughness, where you've got this stylus with a fairly sharp tip, and you drag it along the surface to measure surface roughness. But the guy said it also did absolute measurements, right? It didn't filter out the long range thing. So tried that, grabbed half of the specimen, measured along the surface, and I got this result. And so we're talking about how old we are. This is a strip chart. I don't know if you guys have ever seen this kind of data. You know, it's got a little ink pen on the instrument, and it actually draws this on the chart, and that's your data. There's no, digital analog, nothing, right? I get data on a strip chart. And I was thrilled, though. If you look at this, you can see all the noise from the surface roughness, but you see the zigzag, right? Up, down, up, which looks like that bent beam stress profile. I was absolutely ecstatic that this is going to work. I was sure the answer was going to be right. And by the way, the range on this is half of a thousandth, so about 12 microns. So it's a pretty small signal, but it seems to be there. I was absolutely thrilled. And I went back, somebody told me you could measure this on a CMM. We have those in our machine shops. I went back and measured it on a CMM, got the same basic profile with less noise in it. Calculated the stresses the standard way, built an FE model, which is a 2D model, applied that, forced it back flat. The results are here in pink. The correct answer that I showed you before is here in this kind of dashed cyan. So we're too big by about 60%, a pretty big factor. And I spent, again, this was still a side project. I spent a good month trying to figure out, well, why am I off by this such a big factor? Did the calculations wrong? Is something wrong somewhere? You guys know what it was? Why it was wrong? I know Mike knows, and Adrian I think does too. You guys should know this. So I went and finally I went and grabbed the second half of the beam and brought it to the CMM shop, and I got this result here. Not very much displacement, not much shape. Grabbed that. And once I averaged the two sides, I got the cyan curve, which is pretty close to the results we expected. And of course, we figured out, I had a grad student back then. We didn't publish this for a long time, but right away we did this calculation and figured out how if you unclamped on one side, how much the part moved and how much that would mess up the contour. So it made sense. We understood it. The part where I said this was nearly the last measurement of the contour method was if I had grabbed this half instead of the other half, this would have been my data. So that range is about 4 microns. The shape is not right. And because of my lack of confidence this was going to work, I probably would have given up. So I'm pretty glad I grabbed the other half. Kind of dumb luck. The first real contour measurements were then done in 1999. Identical bent beam specimen, I had more than one of these things around, so then I cut it more carefully, where I clamped it on both sides, analyzed all this data myself, and it was published in the first contour method paper, which I don't think appeared until 2001. The other measurement was done in 1999, was the Mike Hill weld plates, what I always called it, which is shown here. Mike must have sent it to me. We would have been talking, once I had this result, it's kind of when I called Mike, I think, and told him. And we were working on slitting method, doing some other stuff. And I told him, about this method, and I had this great idea, and I think it works. And his initial comment was, yeah, that's great, but I'm trying to do this with a slitting method, and how do we do this, right? It took me a little while to get him excited. Not too long, but a little bit. So he sent me this plate, this weld plate, and I cut it, and I must have done the CMM scan too and sent you guys just the data, probably. The cut was bad. I went to a different EDM shop, and this was kind of a nasty weld, so the cut quality was terrible. Data, I think the data is up there on the wall, right? And you can see all these EDM marks. It's kind of towards the right side there. All these EDM marks, and it was a terrible cut. Sent it to Mike. He had some grad student named Adrian analyze the data. And that's in a report. They published the report in 2001, but I think he started sooner than that on working on that data. In '99, which is kind of before this was published, I had to submit an invention disclosure with LANL. So back then I was submitting an abstract for a conference on the contour method. And back then, all of our abstracts got read by a lawyer for IP issues, right? And I had said, great new method, 2D mapping, first ever, that kind of stuff. So the lawyer says we should patent this. He calls me up on the phone, says we should patent this. I'm not going to let it out the lab. And I said, I don't think you should. I said, you can't patent the method. That's silly, and nobody would ever pay for this, right? And he said, I'm not going to let you show this until you submit an invention disclosure, which is an internal form when they decided they're going to patent it or not. So I filled out this form, and you described the method, and it says, what's the commercial potential? And I said, none. And how much would people pay for this? I said, 0, right? And the guy calls me back and says, okay, we're going to patent this. I said, why? And he said, well, we get judged on this. Our contract with DOE, Landmark, is judged on making some patents. We need about 50 a year, and we're short. So you're going to patent it. Wasted a lot of time with a lawyer trying to explain to them, trying to write this up with a lawyer is pretty painful. Anyways, they eventually did submit the patent. I wasn't too happy about it. You guys proved me wrong, though, on it being worth something. Here's a quote from a physicist about if you have a great idea, people won't believe it. So I submitted this for oral presentation at the ICRS 6, which was in Oxford in 2000, and it was rejected for oral presentation. I called Mark Bork, who ran our neutron instrument, and whined to him, and he was British, so he called back to England and whined over there and got me an oral talk after all that. The proceedings paper for that, which you can get, it's not on my webpage, but I think it is now on ResearchGate. I think it found a thing, and I've got it. Was written before I figured out that if you average the two contours, you got rid of the shear error. So it actually goes through some estimation of what that error would be, right? Which is kind of pointless because you should just average the two sides. But people asked me, the co-author on that was Tony Gonzalez. It was Prime and Gonzalez. And he was the CMM guy that did the CMM measurements. Helped me out quite a bit. He still does them. He's still our lead inspector at the lab. He's also a fantastic black diamond skier. So, Mike and Adrian were working on residual stresses in a single crystal laser amplifier for Livermore, strontium fluoroapatite, big single crystal. And Mike and I must have talked about that, and I talked with the neutron guys, could they do neutron diffraction on this thing? And their answer was, boy, it's a single crystal. We ought to get beautiful sharp peaks and do super precise measurements and be able to map out your stresses. So we applied for beam time. Adrian came out and did the measurements. They were totally wrong. The peaks were horrible. So single crystals have a lot of crystal defects in them, and it makes for these very smeared, horrible peaks. We can get a single stress measurement. I don't know how long you spent actually in the neutron beam taking data, but it was all pretty, several days. Yeah, it was a long time, and it was absolutely useless. Adrian stayed with my family during those measurements in 2002. And so my daughter was about 4. She's a sophomore at UC San Diego now. And Adrian stayed there all week, and my daughter was fascinated with Adrian. He's so conversational at the dinner table, talking all the time. So he was this kind of man of mystery, right? And he was there at breakfast, he was there at dinner. And after the 4 or 5 days, Adrian left. And the next day, my daughter comes and she's looking around, where's this guy? And she asked me, where's the bald boy? We also, on the day Adrian left, I took him fishing in the Hayman's Mountains, which is right above Los Alamos. He wanted to go fishing. And so we took 2 cars because he was going to go right from there to the airport. And I took him to one of my favorite spots and drove him in his rental car sedan out this horrible dirt road with big old potholes in it. Did you get any trouble for the rental car on that? Yeah. It wasn't the best choice. We had a good day at fishing, though. So I want to thank you guys. A lot of the success or popularity of the contour method is more due to how much you guys have done than anything I've done. And I I even sometimes now send my parts to you guys for cutting and scanning. It's kind of funny, but when I do this internally, I have to pay for EDM time. I pay for time on the CMM. And it's pretty expensive, our overhead rates. It's cheaper for me to send them to you guys. And actually, it's faster, too. I have to wait my turn on those machines. And you guys have figured out how to make good cuts, which is really the key of the counter method, right? So your cut quality is always really good. I still like to produce the data myself, so I usually get the data back, and I'm glad that Adrian still lets me do that. While I'm here, some thoughts on the future of the contour method, since you guys do so much. The accuracy of the contour method, I think, is almost all limited by the quality of the cut and cutting assumptions, right? That it's a flat cut or that it's a constant width cut. We were talking about that today, right? It's hard, especially on a part that changes cross-section. The cut width changes a little bit, you get effects. I get all these calls or emails from people who tell me I can measure the surface height better than the way you measure it. I say, I don't care. I can measure it better than I need to know it, because these assumptions are what kill us, right? So maybe someday somebody will find a better way to make the cut than EDM. Maybe. One idea we had talked about, we have that paper, me and Adrian and Mike and Mintran, on the part that fractured. We measured the fracture surface, which is interesting, right? The best quality possible cut would be a cut that's zero cut width and no plastic deformation. And brittle fracture is that. The averaging gets rid of the shape effect, and you potentially get a really nice result. So if you could do a controlled fracture, that would be great. Ceramics, maybe. And I don't think you guys ever measured a ceramic?
Tried it on that crystal.
Yeah. And some ceramics will cut with EDM, but very few. Getting good results all the way to the edges, I don't know how much that comes up for you guys, right? My EDM cuts aren't good all the way to the edge, and sometimes people want that result all the way to the edge. Until you can get a perfect cut, you can do that with multiple methods. I think there's some interesting possibilities there to try and get more data up to the edge if you wanted to do that. The plasticity errors is always an issue, right? Potentially. Always a question, are you getting yielding as you make that cut? And it's very hard to objectively say whether or not you had that effect. So some way to fix that, make it less, or to know it if you haven't, is always great. There's probably some ways to do that. It's not easy. The multiple stress components thing comes up a fair amount. And you guys are already doing that kind of superposition method where you do multiple methods, right? And that works pretty well. Standardization comes up a fair amount, probably more for you guys than for me. People must ask about, is this an ASTM standard? The thought of that makes me cringe. The data analysis, often there's something funny. You got to correct for some artifact, something going on. So that one always worries me. I don't want anything to do with making that standard, but maybe it's a good thing in the end, and you guys can figure out a way to do that, or I don't know. All right, that's my talk. Thank you guys for listening.